Hello and welcome back. Let's continue derivation of some design constants. So let's start with our singly reinforced beam cross section that we had seen. So this is small b, which is the section width. Capital D is the overall depth of the section. Small d is the effective depth of the section, which is depth from the topmost fiber to the centroid of the reinforcement. Now in the previous session we have seen that there exists one neutral axis which separates the compression zone and the tension zone. So let's denote that XU be the depth of the neutral axis from extreme fiber, which is the top extreme fiber. If we come back to the strain diagram, we can note something very important, that strain in concrete at the outermost fiber does not depend on grade of concrete. So regardless of what grade of concrete we are using, the ultimate strain or the maximum strain will be 0.0035 regardless of the grade of the concrete. But that doesn't happen in case of steel. So the strain in steel depends on grade of steel. So that is why this Fy is coming into picture in the strain. So for each grade of steel there would be different value of strain, which we'll be subsequently calculating when we'll calculate depth of neutral axis or limiting depth of neutral axis. So for the time being, let's understand that strain in concrete does not depend on the grade of concrete, whereas strain in steel depends on the grade of steel. Now we have the same stress diagram also. So we have seen in the previous session that we have 0.446 FCK as the outermost stress in the concrete. Now we also have seen that there is parabolic variation of stress in concrete up to the strain of 0.002, and afterwards it becomes linear up to the strain of 0.0035. Now let's denote A as the distance from the neutral axis up to where the strain becomes 0.002. Okay, now what is the interest here? We want to find out what is the value of A and what is the value of XU minus A. In other words, we want to know how much is this distance, which is the distance for the parabolic portion, and how much is the distance for rectangular portion. That is what we want to find out. Now if we find this out, we will be able to get the area of total stress block, and subsequently we can calculate what would be the total compressive force and what would be the total tensile force. So let's write few things down, like we have XU as the depth of neutral axis from top, and A is the distance to 0.002 strain from neutral axis. Please note that the distance is measured from the neutral axis to the 0.002 strain. Okay, so in this case we can apply property of similarity of triangles. So if you can see this one single triangle, which will be XU divided by 0.0035, and there is another small triangle which will be A divided by 0.002. So if I rewrite the same, so it is XU divided by 0.0035, which is equal to A divided by 0.002. So this is from the strain diagram compression zone triangle. Now I'm interested in getting the value of A, so I can switch the 0.002 on the left hand side and rewrite. So I have 0.002 into XU divided by 0.0035. So let's use the calculator and let's see what we get. So it is okay, first of all let's get the fraction. So it is 0.002 divided by 0.0035. So we get 4 by 7 XU. Okay, or if we want, we can get this as 0.57 XU. So we'll substitute that A comes out to be 0.57 XU. So this is the value that we got. Now this A is nothing but the distance of the parabolic stress distribution. So I can now here also substitute that this is 0.57 XU. Okay, now what is remaining distance? So that also we can calculate. Since total is XU, out of that just now we calculated that this is going to be 0.57 XU, so remaining can be calculated. So let's go down and let's get this XU is as it is. So we have XU, and just now we got our A value. This is nothing but 0.57 XU. So that gives us, okay, so let's say 1 minus, just let's get some space here. Okay, so that becomes 1 minus 0.57. So that comes out to be 0.43 XU. So let's write this down. So this comes out to be 0.43 XU. So this is the depth of rectangular portion. So if I go up, I now know both the distances. So this becomes 0.43 XU. So at this point, using the strain diagram, I could find out the distances or the heights of parabolic portion as well as the rectangular portion, which comes out to be 0.57 XU and 0.43 XU for respective zones. Very straightforward calculation from the strain diagram using properties of similarity of triangles. Now the objective would be to get the total compressive force. Now how would I get the total compressive force? I'll have to add this rectangular portion and this parabolic portion. If I can calculate their areas, I will be able to get the total compressive force. So the total area of stress block can be calculated as the addition of area of the rectangular portion of stress block plus area of parabolic portion of stress block. Since we know all the sides now, so let's go down and check what are the areas. So we already know force is equal to stress into area. Now the total compressive force Cu will be equal to area of compression stress block into B into 1. So this is nothing but, this is Newton per millimeter square, because the stress is always having the unit of Newton per mm square. Now this, if I multiply with mm square, I'm going to end up with force which is in Newton. So to get the area of compression stress block, we have to add two different areas. One is the area of rectangular portion and the other one is area of parabolic portion, which you can see in the diagram here, rectangular portion and parabolic portion. So we'll get area of rectangular portion first. So we know area of rectangular portion is nothing but height into width. Now we know one side already, which is this. So 0.446 FCK is one side. The other side just now we got is 0.43 XU. So if we substitute, we are going to get the area of a rectangular portion. So we have height as 0.43 XU and width as 0.446 FCK. So if we multiply, so we have 0.43 times 0.446. So what we get is 0.19. Okay, so let's write this down. This comes out to be 0.19 and this is, okay, the other digit is not significant. So let's multiply FCK and XU. Okay, so this is the product of these two values. It is nothing but rectangular portion area of the stress block. Now similarly we have the parabolic portion. Now area for parabola is 2/3 base into height. Now base we know and height also we know. So let's say the base of the parabola is nothing but 0.446 FCK and the height of the parabola is 0.57 XU. So if we substitute this back, so we have 2/3, base is nothing but 0.446 FCK and height we just now calculated, it is 0.57 XU. Now if we multiply, we are going to get the answer for the same. So it is 2/3 times 0.446 FCK times 0.57. So this gives us the value of, let's say, 0.17. Okay, so this is 0.17 FCK into XU. Okay, so now we have both the areas. We have rectangular portion area, we have parabolic portion area. So if we add them together, we are going to get our final answer, that is the total area of compressive stress block. Okay, so rectangular area was 0.16. If I am correct, let's check. It is 19, not 16. So it is 0.19 into FCK into XU, plus we have the parabolic area, which is 0.17 FCK into XU, which is this area parabolic and this area rectangle. So the total area of the stress block, this would be, so we'll have to add them together. So we have 0.19 plus 0.17, so that comes out to be 0.36. okay, so the total area of the stress block would be 0.36 FCK into XU. So this is total area of the stress block. Now I am interested in getting the compressive force. Now compressive force is nothing but this, what we got is the stress having the unit of Newton per millimeter square. Now I need to multiply with some millimeter square. Let's say this is the area which is in millimeter square, which is including the width of the section and the unit width. So total stress area is nothing but 0.36 FCK into XU. Now I'll add this B. Okay, now instead of writing 1, I'll simply keep it like this. This is our total compressive force, 0.36 FCK XU into B. So this you'll have to remember that the total compressive force comes out to be 0.36 FCK XU into B. And it is very simple to identify. This 0.36 FCK into XU is nothing but the area of stress block, and B into 1 is nothing but the area. So stress into area gives us the total compressive force. Okay, now similarly we are interested in getting the location at which it is acting, because we know the force always acts at the centroid of the area. Now where is the centroid of the area? Because we have two complicated shapes, or one is the rectangular shape and the other one is parabolic shape. So in your earlier semesters you must have studied calculation of centroid for an area, which is nothing but, in this case we need y bar. Now from where we need, let's calculate the distance of compressive force from topmost fiber. Okay, so we need y bar from top. So the classical formula that we have studied for so many years is nothing but A1 y1 plus A2 y2 upon A1 plus A2. Now what is A1? A1 would be the area of rectangular portion, y1 would be centroid of rectangular portion from top of the section. So we already know what is the area of rectangular section, so it is nothing but 0.19 FCK into XU. So let's write this down. So this we already know, this is 0.19 FCK into XU. This is the area of rectangular portion. Now centroid of rectangular portion from top of the section would be half of the height. Now if you see, the height of the rectangular portion is 0.43 XU. Now divided by 2 would be the centroid of this rectangular portion. So we'll go down and let's put the centroid for rectangular portion as 0.43 XU divided by 2. Okay, so that comes out to be, let's see, 0.43 divided by 2. Okay, so that comes out to be 0.22 XU. Okay, so this is 0.22 XU. Okay, now what is A2? A2 comes out to be area of parabolic portion. Okay, so we already know it is 0.17 into FCK into XU. So let's put this down. So we have A2 as 0.17 into FCK into XU. Now we also need to know what is Y2. Now centroid of parabolic portion from top of the section. Now you'll have to see the sketch. Now we want to reach to the centroid of this zone. Okay, so we'll have to cross this and then reach here. Now this is nothing but y1 plus, now the centroid for parabolic section is 3/8 of the height. Okay, so we'll have to add 0.43 XU plus 3/8 of 0.57 XU. Okay, so let's go down and let's put y2 is equal to y1 plus 3/8 of a, which is nothing but y1 we could calculate, which was 0.43 XU. Okay, so this was 0.43 XU, and 3/8 of A is nothing but 0.57 XU. Okay, so let's get 3 by 8 of this. So let's get 3 by 8 into 0.57. This is 0.213 plus 0.43. So this comes out to be 0.64 XU. Okay, so this is 0.64 XU. Now we can use the formula A1Y1 plus A2Y2 upon A1 plus A2. So let's substitute whatever we know. So we know A1 to be 0.19 FCK into XU, right? And we know Y1 to be 0. Okay, let's check, 0.22 XU. Okay, so this is 0.22 XU plus, okay, we'll have to get Y A2Y2. Okay, so let's get A2 and Y2. So A2 would be 0.17 FCK into XU, and Y2 is nothing but 0.64 XU. Okay, so this is 0.64 XU. Okay, so we have A1Y1 plus A2Y2 and divided by, now this is very straightforward to write, it's 0.19 FCK into XU, that is our A1, plus our A2 is 0.17 FCK into XU. Okay, so this is what we have. So if we multiply all of this, the answer comes out to be 0.42 XU. Okay, so that means the force, the total compressive force, acts at a distance of 0.42 XU from top. Okay, so if I go up, I will have to draw a compressive force. Okay, so this is 0.43, so somewhere here, okay, somewhere here our total compressive force Cu acts, and the distance for that is nothing but, okay, it is 0.42 XU. Okay, so we got not only the force magnitude, which is 0.36 FCK XU into B, we also could locate the force just by locating the centroid of the area. Okay, now similarly there is another force which we have to find out, which is the total tensile force. Now again it will be stress into area. Okay, now how do we find what is the stress in steel? So code has told us, okay, code has told us, let's say characteristic strength of steel is Fy. So the code has told us that we'll have to apply factor of safety. Now if you apply, we have done this calculation earlier also, so if we do division of 1 by 1.15, this is nothing but the factor of safety for steel, it comes out to be 0.87 Fy. So the permissible stress or the stress in steel is always 0.87 Fy, and that depends on what grade of steel we are using. For example, we have 4 grades of steel. Mild steel has Fe250, then we have HYSD steels, Fe415, Fe500 and Fe550. Okay, so the stress in steel comes out to be 0.87 Fy. Now what is the area of steel that we are providing? So this is nothing but area of reinforcement that we will be providing. Therefore we already know what is stress into area, and that will give us tensile force. So we know this is nothing but 0.87 Fy. Okay, therefore the total tensile force, the force in tension, is nothing but 0.87 Fy into AST. Okay, now where this would act, we always know the forces act at the centroids. Now it is very straightforward in case of reinforcement because it will act at the centroid of the reinforcement. Okay, so the force, if you can see in the sketch, acts at the centroid of the reinforcement. Okay, now if you see here, the nature of the forces is exactly opposite and they are separated by a lever arm. So if I can sketch that, this is our lever arm. So this is nothing but our ZU, which we can say is the lever arm separating two forces. Okay, now if I can find this out, I'll be able to get my moment of resistance. Now if you can see in the sketch itself, it is very evident that this distance is small d, and out of this we have to subtract 0.42 XU. So this ZU is nothing but d minus 0.42 XU. Okay, so in the diagram itself we could locate the lever arm. Okay, so let's write this down to have our complete set of knots. Okay, so if I go down, the lever arm is nothing but d minus 0.42 XU, okay, which is nothing but the distance of compressive force from top. So ZU, the lever arm, is nothing but d minus 0.42 XU. Okay, so this gives us the lever arm. Now therefore the moment of resistance, if I am taking it from the compression force, so it would be Cu into Zu. Now I know what is Cu. Now the Cu is nothing but 0.36 FCK into XU into B. Okay, and Zu just now we got, which is nothing but d minus 0.42 XU. Okay, similarly if I am interested in getting from tensile force, okay, this is not compressive, this has to be tensile force. So if I need to get it from the tensile force, I'll have to get Tu into Zu. Now I know what is my Tu. Tu is the tensile force against stress into area. Stress is 0.87 Fy and area is AST. That gives me Tu, and the lever arm, again the Zu, is nothing but d minus 0.42 XU. So in summary, we have this moment of resistance from compression side, okay, and this moment of resistance from tension side. Okay, now when to use which moment of resistance, that depends on whether the beam is under reinforced, over reinforced, or balanced. Okay, so that requires some additional calculations and calculation of some design constants that we'll see in the next session. Thank you.